we are beginning chapter 12, and we're not going to do the whole chapter, but we're just going to take a peek into some of these ideas. We're going to talk about vectors, and we're going to talk about the geometry of space, and that's where we're going to begin, is with the idea of space being three-dimensional coordinate systems. So we so far have been working with x and y. Here we're going to work with x, y, and z, and we're just going to get a little peek into this. This is usually where Calc 3 would pick up. Calc 3 often has the title multivariate calculus, and that multi in there means extra variables, multivariate. So many variables, which then brings in that z variable. So we're just going to introduce this idea a little bit here, not go super in depth with it. So a three-dimensional coordinate system in x, y, and z is said to be a right-handed system. And that means if you hold up your right hand in a fist, then the direction of the finger curl points the x-axis, out your wrist points the y-axis, the positive of each of these, the positive x-axis, the positive y-axis, and your thumb makes the positive z-axis. So that gives the direction then of the graph and where we would find those positive variables. So in 3 dimensions then we can graph planes of a single variable. So if we just have x, y, or z, that'd make a single variable, horizontal or vertical plane. We can move those around by just giving variables to or values to 2 of the variables. We're not going to be working in the graphing in 3 dimensions, but just a couple pictures here. Now, really, all of these so far are just 2-dimensional graphs just put onto a 3-dimensional system. So a plane is still a 2-dimensional object, or in these, a circle is a 2-dimensional object, but put into the 3-dimensional system means that we can raise that circle up into the z values. So our first concept of calculation that we're going to do is finding the distance between 2 points in space. So finding the distance between 2 points in a plane, we can use the Pythagorean theorem. And that's really what this is the Pythagorean theorem again, but with that third variable brought into it. So it says the change in the x and the change in the y. We square those. That's like the x distance, the y distance, square those and add them together. We should get that hypotenuse distance squared. Well, same thing here, except bring in the z variable. So we're going to take all those differences, square them, take the sum of that, and take the square root. So it's like an extended Pythagorean theorem. And this is kind of the picture of that idea, and they also cite using the Pythagorean theorem for that. That's an example that we're going to actually do. A sphere is like the 3-dimensional extension of a circle. So it's the set of all points that are the same distance away from a central point called the center. And this equation is much like the equation of a circle. So the equation of a circle, we have x minus the center value squared, y minus the center value squared equals radius squared. Well, same thing here, except we're going to bring in that z variable. And we'll look at that example with step-by-steps. And so now we're ready for those examples. All right, so in our first example, we are going to look at the points 2, 1, 5. So it's a really messy 5. I'll try to write that better. 5 and -2, +3, 0. So those are our x, y, z points, and we want to find the distance between those 2 points. So to find the distance between those 2 points, I'm going to use that extended Pythagorean theorem and say that it's the square root of how far apart are the x's. It doesn't matter which way you do the subtraction, whether you take x2 minus x1 or x1 minus x2, as long as you're consistent. So it really doesn't matter. So I'm going to do 2 minus -2. I'm taking the first point minus the second point. Square that. 1 minus 3. Square that. And for the z's, 5 minus 0. Square that. So I get the square root of minus a negative, so 4 Here I get -2. Now if you're going to type this in your calculator, I'm sure you know, but just in case, make sure you do put those parentheses in there, because if you type in a -2 without parentheses squared, it's going to say the answer is -4. But a -2 with the parentheses squared, which is really what we want, that is -2 times -2, which is +4. So add that all up, and we get 45 under that square root. That's not a perfect square, so we can just leave it at the square root of 45, or if we wanted a decimal approximation, we could get that. All right, so that's distance. It is taking the Pythagorean theorem and just extending it out by one more variable. Our sphere equation, what we're going to do is take an equation that is not in standard form, rather it's in what we call general form, which is just the listing of all of the variables and the constant all on one side of the equation equals 0. And now from this, you cannot just look at this, I don't think, and tell where the center is and what the radius of this sphere is. So what we're going to do is rearrange them now. I'm going to take the x variables and I'm going to group them up and intentionally leave a space, plus the y. Well, there's only one y variable, it's just the y squared. There's not a linear y, so just leave that. And then the z, we got z squared and minus 4z, and I'm going to leave a space, and I'm going to say that is equal to, and I'm going to subtract that 1 over to the other side there. Okay, now what we're going to do is we are going to do what is called completing the square. In that purple group for the x, if I have 3 x's, I'm going to split those equally, because in geometry we know that a square has equal sides. So I'm going to make the two sides of this equal to each other. So then that would give me factors of x plus 3/2 on both sides. So that's x plus 3/2 times x plus 3/2. But in doing that, an extra value shows up here that completes the square. That's why it's called this. Where if we multiplied those together, we would get 9/4. So I need to complete that square with a 9/4. We can do whatever we want in an equation as long as we do it to both sides. I just added 9/4 to one side of this scale and it started tipping, so I need to go add 9/4 to the other side of the scale as well so that it doesn't tip. All right, now we're gonna do the same thing for that green group. I've got z squared. I've got minus 4z's, so I'm gonna split those equally, minus 2z for both of them. So that gives me factors of z minus 2, and I have 2 of those factors. But in doing that, another number shows up here. -2 times -2 gives me +4. +4 completes that square, tipping the scale, so I need to add that 4 to the other side as well. Then the y, it didn't need to be completed because it was only the quadratic part there. Now on the other side, when I add this all together, I could get some common denominators there of fourths, and this adds up to 21/4. All right, so now this is in what we call standard form for our sphere, and our center is going to be located at the opposites of the numbers in each of those parentheses. So -3/2 is the x-coordinate, 0 the y-coordinate, and +2 is going to be our z-coordinate. And our radius is going to be the square root of 21/4, which we can simplify a little bit and just make a square root of 21/2, since that 4 is a perfect square. Okay, so standard form of a sphere, like a circle, is each variable minus its centered value, and that's equal to the radius squared. Okay, So just a little bit about working with three variables here. And in the next lesson, we're going to look at vectors, and we'll look at vectors with both 2 and 3-dimensional coordinates. All right, have a great day.